Good morning to one and all present here. I am Dr. R. Amaleshwari, Triple Department Assistant Professor. So now we are in the third day of our FDP, recent trends in electric vehicle technology. So till now we had seen the topics on power converters for EV and its interfacing challenges on first day, followed by vehicle to grid and grid to vehicle technologies. Today we are having our esteemed guest from NIT Pondicherry. So
subjectively. Good into this.
Sir, maybe question papers there.
I'm sorry for the inconvenience caused.
Sir, file.
Today we are having Sir Dr. Hemchandra sir from NIT Pondicherry covering the topic electric vehicle electronic perspective. So I request our HOD sir, Dr. R.S.R. Krishnam Naidu sir, to speak few words regarding this. Over to you, sir. Please unmute, sir. HOD sir.
1 minute. Okay. Sir, good morning, sir. Hemchandra, sir.
Hello. Sir, am I audible?
Yeah, audible, sir. Audible.
Yeah, thank you.
So, good morning, sir. Thanks for accepting our invitation today. Ladies and gentlemen, very good morning and welcome to the third day of our faculty development program on recent trends in electric vehicle technology. Today, we are honored to have a distinguished resource person, Dr. Hemchandra sir, from the esteemed National Institution of Technology, Pondicherry.
Yes, ma'am.
So I would like to thank all the participants to actively involve in this FDP and giving your valuable feedback here. And please kindly enhance your knowledge with this faculty development program with the resource persons. So thank you, sir. Once again, I am welcoming you. Thank you very much.
Sir. Thank you, sir. Thank you for inviting me.
Yeah, thank you, sir. Amaleshwari ma'am, please continue. I request Dr. Amaleshwari ma'am to read out the one-page profile of the today's guest.
Sir. I received BTech Electrical Engineering from Telugu Engineering College in 2012. The ME from Power Electronics and Drive Control from Andhra University in 2012 and PhD degree from NIT Jaipur in 2020. He is currently working in electrical engineering departments in NIT Pondicherry. He published 8 papers in international journals and 2 papers in international conference and 3 book chapters. For the design and development of high power density wideband gap devices based on DC-DC converters for 2-wheel and 3-wheel EV application. It is funded by MEITA Government of India. He shanks and is in the progress. He delivered more than 15 guest lectures in various institutions and a review of IEEE transactions on industrial electronics and IEEE transactions on power electronics and IET Power Electronics and IET GTD. He is a member of IEEE and associate member of IEI. These areas of interest include multi-port DC-DC converters, their control, and fault-tolerant DC-DC converters for our renewable energy systems and battery management system. Sir, Ramchandra, sir.
Yes, ma'am. Yes, sir. Can you start?
Yes, sir, continues.
Yes, sir. Thank you, sir. Thank you for giving me this opportunity to interact with you. And thank you for good, wonderful introduction, sir. Thank you very much. So, sir, can you please enable screen sharing for me?
Screen share.
Yeah.
Okay, sir. Sir, one check.
Yeah, sir. Right. Sir, is my screen visible?
Yeah, visible.
Thank you. Sorry. Yes.
Okay, sir.
Yeah, thank you. Yeah. So in today's session, we'll cover the power electronics perspective of electric vehicle. Not much into that, but yes, I'll try to cover the basics, why, what, and how these power electronics are growing in the electric vehicle technology. So even before that, the first half of the session will be mostly related to electric vehicles, and the basics of electric vehicles. Most of you might have known this, but just a quick review of that. So as you know, electric vehicles are growing in the market, and it has already reported some 16% of annual growth. And now the concentration is more on four-wheeler and public transport. So already there are various companies which have come up with buses for public transportation, and I think recently some buses have also been allotted to Andhra Pradesh from Tirupati to Tirumala, that Ghat road. The basic scenario how the electric vehicle market is going in the recent, from the last 2 to 3 years to the next some 10 years, it is like Government of India aims by 2030, 100% of the two-wheelers should be EV, 100% of the three-wheelers should be EV, 100% of the four-wheelers should also be EV. However, it takes a lot of time to improve this public transport and all the other buses. So they are expecting at least some 40 to 45% of electric vehicles in public transport. And if you have recently followed the news, as I said, some buses have been allotted to Andhra Pradesh from Tirumala to Tirupati they are using. And next is recently Telangana government has also started I think Garuda buses from Hyderabad to Vijayawada. Some 6 buses they have launched, and all the 6 buses are electric vehicle buses, completely run by batteries. So why people are going with that? As you know, the pollution concerns and the prices in the petrol and diesel hike. So these are all main reasons. However, if you see the last few years statistics, there has been a very huge market. You can see that there is a very huge market, or a very huge improvement in the market from the last 3 years in the electric vehicle domain. Just statistics to show. And yeah, why are we still lagging in this electric vehicle market? Like, most of the countries have already been completely transferred to electric vehicle. However, we have not yet done that. And the major reasons what limits the usage of electric vehicles are, the first one is driving range. So few electric vehicles nowadays which are coming, they are giving a very high driving range of up to 400 kilometers. But initial electric vehicles, they were having a very low driving range 100, 120, 150, 180, something of that kind. But nowadays, yes, of course, it is increasing. And second is cost or price premium. That is, now if you go and buy normal Tata Nexon, a mid-range Tata Nexon, it is costing you somewhere around 14 lakh, around 14 lakh. But if you go with electric vehicle of the same company with the same feature, the Tata Nexon, it is costing you somewhere around 19 to 20 lakh. So the high price, the premium price is what people are still thinking of. And of course, there is lack of electric vehicle charging infrastructure. As you know, this is one of the basic and major reason why people are not shifting to electric vehicles. And of course, the second is time required for charging. So the time required for charging, it is very high in normal batteries. It takes somewhere around 7 to 8 hours. Whereas in fast charging batteries, even it takes somewhere around 2 to 3 hours. So people cannot wait till that time to make their task done. And of course, you have already seen the recent accidents with two-wheelers, especially two-wheelers. Yes, sir. Any issue? Right.
Yes, this is the one time. Again,
So the safety concerns with battery, now you have seen recently Ola, as well as some e-Pluto, many bikes have been just burnt out simply like that without any proper reason. Recently in, I remember it in somewhere in Hyderabad or somewhere in Warangal, the people are sitting on the bike. Suddenly they noticed that electric bike, suddenly they noticed fire and stopped simply just within a fraction of second, the complete bike has been burnt out. So these are various issues related to the safety concerns with the battery, why people are not even trying to go with that. And some vehicles, especially these goods carrier, people are not very confident that electric vehicle can drive a goods carrier vehicle. So people are not preferring that. And of course, some will be very peculiar about brand of the car or brand of the two-wheeler. So that brand has not yet released, maybe that brand has not yet released their EV. So people might be waiting for that. So these are the various reasons, the major reasons why people are not using electric vehicles. And one of the main reason is, as I said, the lack of electric vehicle charging infrastructure, which is our main concern now. Now, why there are no proper electric vehicle charging infrastructure? See, even before going to four-wheeler, just take a simple two-wheeler. Now, if you go to a two-wheeler, if you see, there are 4 models of Hero electric bike: Hero Photon, Optima. In Optima, again, 2 models, HX, LX, and in Hero Flash. Now, if you see, all the 4 have a different battery specs. So one is 72 volt, one is 51 volt, one is 48 volt, one is 20 Ah, one is 30 Ah, one is 26 Ah. Similarly, if you go with Okinawa, that also the same thing: 72 volt, 60 volt, 48 volt. If you go with Ampere, again 48 volt, 60 volt. See, the company is same, but the battery specifications are different. So each battery has its own voltage rating and the capacity rating, that is AH rating. Now, how can I install a charging station for a single battery? If I go with some 48 volt batteries, only if I'll charge only 48 volt battery, I don't know how many vehicles will come. So there are various reasons, and this is the main reason why electric vehicle, at least two-wheeler charging stations, are not very popular in the market. The same can be related with this four-wheeler also. So some are using 200 volt battery, some are using 380 volt battery, some are using 270 volt battery for some four-wheeler, and some are using 400 volts battery. Now again, when the battery rating is different, you cannot have a single or a uniform charging capacity or charging station to have all or to charge all these wide range of vehicles. So that is the major reason why electric vehicle batteries have not, charging stations have not come into existence. Now, coming to the roadmap. So this is the roadmap by Niti Aayog and Ministry of Power in India. So by 2030, as I said, they are interested in coming out with complete or complete 100% electric vehicle mobility or e-mobility. Now, what are the, if you go through the facilities, what are there for development of a charging infrastructure? So the first one is you should set up a charging station, which you call it as a public charging station. So this public charging station is something different from some charging stations which are in existence now. Maybe in 2014-15.
ఎవరికి ఇలా లేరు చెప్తే వినేలాగా పేరెంట్స్ అంతా
Sir, somebody please mute yourself. Yeah. So when now if you go to in 2014-15, yes, 14-15, I think when Andhra Pradesh has been newly formed, the government focus was mainly to.
Hello.
Yes, hello. The government focus was mainly to what you call improve or increase the e-mobility, and based on that, all the higher officials of APPDCL, commissioners of various municipalities, all these have been given with electric vehicles, and to charge these electric vehicles, nearby substations have been used. So if you go to some substations in and around Visakhapatnam even, you can find a charging station, electric vehicle charging station, which is not open to public. That is specific to those electric vehicles. Mostly they have been given with, I remember it is Tata Tiger EV they have given, and Mahindra E-Verito they have given. They charge only these particular vehicles. So if you wanted to visit one such kind, you can go to Sitamdara substation, and one more is in Gopalpatnam substation, and yes, Gajwaka substation also. Commissioner, GVMC commissioner office also you can go. So there are some particular points where they have already set up these charging stations which are not open for public. You cannot use them. That is only for their purpose. So now people are coming forward to open this public charging station. In order to use this, what the public charging station or where it should be installed, as per the government regulation, for every 25 kilometers there should be one charging station on road, and for every 100 kilometers you should have a fast charging station. So this is what is government planning to, and phase 1 and phase 2 are already started, and phase 2 is in progress. So the phase 2, as per this phase 2, I think people are now in relation or in relation with this, in line with this phase 2. However, it needs to be speed up. And the major issue with this electric vehicle charging station is how to charge. How to charge in the sense, what should be the tariff? Now, if you go with your home electricity tariff, it is very easy, simple. Like you used to get one, what you call, you'll have one, you'll get the current bill, and beside the current bill, they used to write what is per unit charge, 1.35, 2 point something based on your units consumption. Whereas what it should be for public service, public charging station, that is not yet finalized by the government, because in each state we have different unit price, and that cannot be
Being sorry,
cannot be made common. So even before starting further, these are some basic definitions of electric vehicles related things. One is electric vehicle supply equipment. So that is nothing but which supplies the electrical energy for the charging of the battery vehicle. Public charging station, battery charging station. This battery charging station, where the discharged or partially discharged electric batteries are electrically charged. As I said, this is not public charging station. It is only related to something like this captive charging station, like in particular domain, particular office only can use that. Next is battery swapping station. So you can take, you can give your battery and take one more battery from them, a new battery or a charged battery from a swapping station. And again, battery swapping stations are not very famous in India. The major reason is, again, there is no proper standard that is being followed with respect to batteries, the ratings of the batteries. That is why these battery swapping stations are not very famous. Whereas in Pune, there is one startup which has its own two-wheeler, three-wheeler, and a battery swapping station. So the battery rating and all are very, very specific. And the same battery is used for all the two-wheelers, and three-wheelers have a separate battery. And whenever you feel that the battery is almost about to die, you can approach the nearest swapping station of the same company. You can give your battery and you can take a fully charged battery. They take some nominal charge for that. So these are the different types of charging of the battery, charging of electric vehicles. One is AC level 1, where it is as simple as that 120 volt single phase, whereas of course this is not for our purpose, this is other level. AC 2 level is what we use generally we use in our homes, 240 volt single phase AC with 12 to 80 ampere. Of course, we are not going beyond 12 ampere. And DC fast charge, this is very, very important, and this is what people are looking out to come out with a solution for some fast charging stations. So these are the various rated voltages and what the Indian standards or guidelines tell. So for a fast charging station, you should have a CCS type of charger, which is rated at some 200 to 750 volts, and one charging gun. CG is the charging gun or connector gun. So mostly we are going with a small or moderate or slow or moderate charging station. So in case if you find any AC charging station, it should have 3 connector guns, each of 3.3 kilowatt, and the rated voltage should be 230 volts. So these are some of the guidelines and the guidelines for charging infrastructure. And these are some charging time and the power level and the standards what Indian government has given, and Indian government through BEE, Bureau of Energy Efficiency, it has given. So here if you see, we are mostly concentrated in here you can see in fast charger, this one, sorry, this one, fast charger, because you can see the battery, for a four-wheeler, the fast charging, the typical charging time for a four-wheeler of 15 kilowatt hour is 15 minutes, hardly 15 minutes. So this is what people are actually looking for. If you can go with this kind of charging station, if you can establish this kind of charging station, it will be very, very easy and very, very easy, and people will surely adopt to the electric vehicles. So what are the major issues that are associated with the development of charging stations? So here coming to the first thing, most of them are working on, maybe most of them are working on this voltage stability harmonics. You might have heard about this, but remember, whatever we study in in power system, it is only of a certain aspect. But if you connect a very heavy load like an electric vehicle, and that too a non-linear load, in that case, it is very obvious that the complete voltage stability will collapse and there will be very high harmonics injected because they are non-linear loads. So now you need to handle these non-linear loads. In order to handle these non-linear loads, what are the solutions you are having? You just have a literature survey and then come out with a proper solution. Then you can implement the same solution in a charging station. This is another reason. Now, where should I have a charging station? Now, I cannot have when you wanted to establish a charging station, it is obvious that it requires some investment, a huge investment indeed. So if you can compromise on some aspect, like if you wanted a land at a cheaper rate. Now, on the main road, you cannot get a land for a cheaper rate. So you will go somewhere inside. Now, inside, nobody will come to charge the vehicle. So you need to have a very optimal location to charge your electric vehicle. And some of the optimal locations for two-wheeler and four-wheeler are parking lots in shopping malls, hospitals, movie theaters, etc. Because when people come for a movie, for 2.5 to 3 hours, they'll charge their vehicle, they will watch the movie, or they'll do their shopping the vehicle will be getting charged. So these kind of facilities should be provided in shopping malls, movie theaters, and hospitals, where that will be one optimal location. And the second optimal location, as the government has suggested, on the roadside, for every, say, some 5 to 10 kilometers or at least 25 kilometers. So when it is charging for every 5 kilometers, it should compulsory have its own transformer. It should compulsory have its own transformer. One second. Yeah, sorry. It should have its own transformer. It should have its own setup. So in that case, the complete voltage instability will occur and also will disturb the regular power flow. Now, this uncontrolled charging will increase the demand during some particular time and may increase the overloading of, may result in overloading of the transformer also. That means, suppose I wanted to charge, I have an electric vehicle charging station, say somewhere near what you call Siripuram junction. Now, when we have a charging station at that point, you know, at 10 o'clock or at 9:30 or somewhere around 10 o'clock, all the shops will be on and there will be a sudden rise in the demand, the load demand. At the same time, if I charge some 4 or 5 electric vehicles at the same time, that will further increase the peak load demand and the transformer will be overloaded, resulting in tripping of the circuit or tripping of the transformer. So this kind of thing should not happen. So you should have some controlled charging infrastructure and controlled charging pattern. Because of this, what happens is the cost will be increased, the degradation will happen for the components which you use. And the distribution networks, what are there in India as of now, they don't have an experience of electric vehicle charging station. And the distribution networks need to be either rearranged or rebuilt, or you should have an alternative to the distribution networks which run only for electric vehicles, which is very difficult task. So again, as you know, when we are going with this fast charging stations or even charging a battery is a DC source and you need to convert the AC to DC. So again, when you convert AC to DC, again, there will be problems like harmonic injection of harmonic, power factor correction. There will be various problems that occur. So in order to, you should see that these all problems get suppressed and there should not be a very high impact on the grid side because of these charging stations. So these are the main issues that are available or that are associated with charging station development. Now, are there any other solutions available? Yes, there are. So I'm showing you a simple solution. 1 second, just yeah. So this is by Semicron. Yeah, this is by Semicron. I'm not advertising anything. I'm just telling you what actually is happening with industries also. So this Semicron has charger solution. So this is a car charger station solution. So here, everything like this is the infrastructure they have taken. Maybe, yeah. So this is the infrastructure they have taken. From the grid, they have a transformer, a rectifier. Again, they can charge 3 number of cars at the same time. If you want, you can have multiple numbers also. The solution is available for multiple level. Here you can see some dots, which is multiple. So for every, from the same rectifier, they have a different control unit and a DC-DC converter to charge this. And these DC-DC converters are all, all these converters are isolated converters. And the control unit will, as soon as you plug your charging point into the vehicle, the control unit will sense the state of charge of the battery the voltage of the battery, the rating of the battery, and accordingly, it will manage the voltage and current into the battery. And once the battery is fully charged, it automatically cuts off from the supply. This is how this Semicron has developed their model. And in the input side, there is one line rectifier. Now, this line rectifier is not a normal three-phase diode rectifier. They have used a active front-end rectifier. That is, actually, if you see this rectifier with these diodes or thyristors, the diodes, as you know, it is an uncontrolled rectifier unit, whereas this thyristors, if you use, as you know, again, it involves lot of cost as well as lot of complexity, because thyristors are not self-commutated. You should commutate. You should use some extra commutation circuit. You might have learned class A to class F commutation circuit. One or the other you should use to commutate it and then convert it into DC. Whereas this is an active front-end rectifier which uses IGBT. Now, as you know, these IGBTs, the advantage of IGBTs is they can switch at a very high frequency when compared to your rectifier, thyristors. And if you use thyristors, you have no other option except to go with 50 hertz frequency, because you should have natural commutation. If not, you need to use another commutation circuit. So the maximum frequency you can use is only 50 hertz. Whereas in case of thyristors, you can go with fast switching, which reduces the filter size, the filter requirement, improves the quality of the voltage across the output, and many. So in order to go, in order to use these advantages, they have used this active front-end rectifier for this purpose. And as I said, this is the DC-DC converter with a galvanic isolation. That is an isolated DC-DC converter, which you call it as DAB, dual active bridge. So this dual active bridge is one controlled DC-DC converter where you can actually regulate the voltage injected into the battery or voltage applied to the battery, current injected to the battery. So you can regulate just by operating or changing the duty cycles of these IGBT switches. So this is another advantage. Next. So they are also working on this wireless charging, using the concept of induction. I think 1 second. Yeah. Yes. So this is the concept of wireless charging, where you have a charging station and your battery is also connected to a similar type of connection, but it is not connected electrically. It is magnetic coupling. So this is how this, inductive charging. So this is what is happening in the charging station. So this is one commercially available solution. So if anybody is interested to have one charging station, you can get the approval and you can approach them. They will give everything, they will arrange everything, and they'll go. So this is how it looks like, your charging station looks like and as I said, this is by Semicron. Now, similar type of architectures and similar type of solutions are also available with ABB, are also available with Infineon, and many companies have these, or many commercially available products are there. But again, still the problem remains these things what we have discussed. That is, these issues still remain. So now this is one of the major research areas where one can work on. So this is a simple architecture of a battery vehicle, as you can see. So here is the battery. From the battery, we have a DC boost converter. From the boost converter, we have an inverter, and then to the motor. Because most of the motors which are working nowadays are either BLDC or SRM or PMSM motors. Mostly SRM and BLDC are widely used. So we need this inverter and boost converter to, as you know, to enhance the voltage of the battery. And these DC loads, whatever are here, these are your auxiliary loads, like your headlight, your horn, your wipers in a four-wheeler, signal lights, Even sometimes now people are shifting to use this AC on this battery in four-wheeler and so on. So this is a simple architecture of an battery-based electric vehicle. And nowadays, another concept of hybrid system has come into the picture. So hybrid, you use PV and battery to run your motor. So PV cells and a battery are connected in this way, and you have a DC-DC converter here, which is fed to the inverter. And similarly, you have a bidirectional converter which is fed to the inverter from the battery. And this bidirectional converter is used here because during what you call braking is nothing but you're decelerating your vehicle. In such case, we have studied the concept called regenerative braking. So during regenerative braking, you're allowing the motor to charge your battery. You're allowing the motor to charge your battery. So the power flow will be from motor to battery. Similarly, when the battery needs to be charged, you should have your PV cells also, your PV cell should also charge the battery. So this bidirectional converter is used to charge and discharge your battery. And you also have a DC-DC converter to supply the auxiliary loads. These auxiliary loads are nothing but, as I said, the light, headlight, tail light, signal lights, wiper, air conditioners, heaters, etc. in a vehicle. So this is a simple electric vehicle power circuit. And these are some electric vehicles that are available in India with their battery capacity and range in general. This is some not very famous, but yes, some vehicles that are available in India as of now. And you can see this Tata Nexon and Tata Tiger have, of course, they claim their range to be somewhere around 312 to 306 conditions. As you know, star always there, that is terms and conditions, the driving cycle, the drive cycle, and everything matters. So these are the charger types. Now, as you see, the chargers are not actually manufactured in India. We are getting from here and there. So this is how the charger looks like in Japan, USA, Europe, China, and remaining market. This you call it as Tesla charger. And these are the charger type and the voltage and capacity levels, what is shown in this table. So these are the CHAdeMO type charging guns, which are available in India. So this, if you go to any charging station, in case if you have any charging station nearby, you can visit it and you can see this. It will be something like this. So this is another type of charging station, and this is what is the charging station that you find in any of the captive charging stations, that is any of the charging stations in nearby substations or some government offices. This Hexacom company has installed them. So in case, if possible, you can have a field visit to that. At least the students can go and visit this charging station. They don't tell anything, just if you wanted to visit it. Yeah. So here they can charge at the same time. They can charge. This is another AC001, where you can charge three vehicles at the same time. This is a kilowatt. So these are charging stations in charging guns or connectors, whatever you call, for different AC and DC connections. Now coming to the battery types. Now coming to the battery types in electric vehicles, mostly we are using lithium-ion batteries, lithium-ion and lithium-ion phosphate batteries, whereas Tesla is very, very particular to use lithium nickel cobalt aluminum oxide NCA batteries, which have a very high specific energy density, with specific energy as well as energy density, and of course the safety is also very good. However, we are not concerned about all this we are mostly concerned about cost and life cycle. So we are in general Indian market is going with only lithium ion phosphate cells, where you have a very high life cycle of 1000 to 2000, and energy density is also a bit better, and specific energy is also a bit okay. Recently, these NMC batteries have also come into the picture, which are having a very good performance compared to lithium ion phosphate. Of course, when they give a good performance, you should agree that you should have a good, I mean, you should be ready to spend more amount cost on that. So coming to the types of chargers, there are two types of chargers. One you call it as onboard charger, and the other you call it as offboard charger. So this is a conventional onboard electric vehicle charger, where this is the charging station, the AC charging station, and the AC supply will be, so this is the charger where you have a rectifier unit. So the plug, whatever you have seen, the connector, whatever you have seen, when you plug it into the charging station, when you connect it to the battery, first AC will move to the rectifier, the AC voltage will get rectified, then it will go to the DC-DC converter. So it will be having several DC voltages, and it is given to the protection circuit. This protection circuit will actually give command to charge the electric vehicle battery. And nowadays, this CCCV charging is becoming dominant. So this CCCV charging, it means up to 80 or 85% of the SOC, the battery will be charged in constant current mode. And after that, 80 to 85%, the battery will be shifted to, the charging will be shifted to constant voltage mode. The reason is to improve the performance of the battery. So whenever you have a battery, obviously you will have some BMS in it, that is battery management system, which take care of many things: the SOC of the battery, the temperature of the battery, the voltage of the battery, the current of the battery, the health of the battery, everything it takes care of. And this BMS will give command to the protection circuit whether it can charge further or not, whether it can, if it can charge, whether it should charge in CC mode or CV mode. So all the command to the protection circuit will be given by the BMS. And also it has some power control unit also. So this complete setup, we call it as a onboard electric vehicle charger. And this is how your onboard electric vehicle charger is placed inside your four-wheeler. So if you see the four-wheeler, so the motor and drive is on one end. This is the transmission system, and here you can see the battery pack, and here you have an onboard charger where first initially it is going to the filter. So this is a general block diagram. However, you need to take care of EMI, EMC also. So there is a EMI filter, and from there on the story repeats. So this is an integrated onboard charger. Nowadays it is now, in case if you go with recent literature, there is a concept called integrated battery or onboard charger. This integrated onboard charger, it is nothing but, instead of using a separate what you call elements like inductor for the purpose of DC-DC converter and everything, we already have a motor and motor windings. Now, when we are charging battery, it is obvious that we don't use motor drive. So we try to use that motor windings as inductor for the purpose of charging. So this is the new concept, what we call it as integrated onboard charger. And these are the various configurations that are available in the literature for electric vehicle onboard charger. So here you can see, here you can see you have an filter. Along with that, you have one boost power factor connection. PFC stands for power factor correction, which means in case if there is any, see here we have a rectifier load, and again we have a non-linear load. So it is obvious that, and you have used many switches, so it is obvious that the power factor will not remain unity. So we should always try to remain the make the power factor unity. So for that purpose, we use this power factor correction circuit. So this is one such kind, and this is another kind of what you call onboard charger. This type of onboard charger generally it is used by Tesla in Tesla cars, and this is the third one. It is used generally in this Hyundai cars, and the last one it was developed by GAN Systems or Hella Electronics. So these are different types of onboard chargers or classifications of different types of onboard chargers that are available in the market right now. And these are few integrated onboard charger. As I said, see here, the machine winding itself is acting as inductor. See here you have different inductors available, or there are different inductors that are used for different purposes. It may be filter, it may be boost converter, or it may be this what you call DAB, whatever it is. However, in integrated type, as I have already told you, the motor winding will be used as the inductor. So there is no separate inductor for the machine. The windings itself act as inductor, or during this charging purpose, the windings will be made to be used as inductor. So there is no separate requirement of inductors, and that is one of the major advantage of this. So these are again available in the market. This is used by Renault, Valeo, Continental, and this is a general traction integrated charger. Now coming to the offboard charger. So this onboard chargers, as you see, the difference between onboard charger and offboard charger is onboard chargers you feed AC supply. So AC supply, the charger inside the vehicle itself consists of, whereas the offboard charger it is different. The charging station has everything in it. Only DC supply should be fed to the battery. So here the charging station has everything. So the charging station has the supply, rectifier, converter, and finally you'll be having one controlled DC supply. This controlled DC supply will be used to charge the vehicle. So this is the vehicle and this is the charging station. Now, this DC supply, which is coming out from the charging station, you cannot directly feed it to the battery. It is obvious that you need to sense what amount of voltage should be given, what amount of current should be given or taken from the battery, taken by the battery, and what is the thermal capability, and so on. So it is again your BMS which plays a major role. Now coming to this DC supply, where you can have up to 700 volts DC supply. It is possible using your fast charging station or a offboard charger. And generally these offboard chargers can be also termed as fast chargers because you are not feeding AC, you are directly feeding high voltage DC to charge your electric vehicle. And these are various offboard chargers that are available in or that are developed by various companies. So the first one, it is developed by so in the charging station itself, you have this complete arrangement. Only you will have battery pack and you need to connect it. That's all. So this is developed by ABB, the first one and the second one. The top two are developed by ABB. So again, this is one type and this is another type. This is an interleaved bus. Now, why are we going with interleaved? It is because whatever the what you call voltage and current ratings are there, that will be very, very high. So when these are very high, you should have your inductor capable of what you call managing that high current. However, if you wanted the inductor of a very high current capability, the size of the inductor will increase very, very rapidly, or the size will be very, very high. So in order to decrease the size of the inductor, we generally go with interleaved. So interleaved, what happens is, after coming to one particular point, there will be 3 inductors connected in parallel. So the complete current will get distributed in all the three inductors. So the stress on single inductor will be very less. So because the stress on single inductor will be very less, the heating effect and the losses will be very less when compared to the conventional high current carrying converter. So this is what is interleaved buck. And this is another one which is developed by the Porsche, again, which is a fast charger. And this one is also by Porsche, and this one is by Tesla supercharger, which you call it as a fast charger. So if you see all the configurations, all the 5 configurations available in off-board charger, they are fast charger, because you are not feeding AC to the battery, you are feeding directly high voltage DC to the battery. Next. Now, this is how whatever we have seen now we'll try to relate with our power electronics perspective. So the first one, what we have seen is the charging station. So the charging station, if you wanted to develop, you have understood the charging station scenario, where, what should be there. And if you see each and every component, it may be inside the vehicle or outside the vehicle, involves power electronics. So you have a rectifier, you have a converter, you have a control unit, you have a charger controller, you have CCCV charge. Everything is related to the power electronics. And as you see, where there are various topologies that also have come out with this or come out for this purpose, which are again related with power electronic converters. So if you want to do some area research in this area, one of the best options you have is power electronics and its application for electric vehicles. And another important area of work or research in electric vehicle is your charging, optimal location of the charging station. So based on this all input, finally I have come up with some research scope in electric vehicle technology. So the first one is, as I said, it is the charging station, fast charging station. Now charging stations have almost reached the saturation because people are always going towards this fast charging stations. As you know, people will try to adopt fast and smart into the culture. Next is ultra fast charging station. Next is development of these DC-DC converters using WBG devices, that is wide band gap based devices. So these wide band gap devices are nothing but, so as of now, what we are using, the switches what we are using are MOSFETs or IGBTs, which are made with silicon. Now people are shifting towards the latest technology called wide band gap, where the band gap between the valence band and the forbidden band will be more, which ensures high or more what you call power in less volume, which you call it as power density. So the power density will be very high in case of WBG devices. So here, if you wanted to just take any of the structure, if you want structure on PCB, say it comes the size of your notebook if you use silicon diode. Whereas if you use these wide band gap devices, it comes to the size of your notepad, not notebook. So you see the drastic improvement in the size. So the size is decreased. And further, the normal silicon devices can operate up to a maximum of 75 degrees centigrade. Whereas these WBG devices can operate up to 175 degrees centigrade or 150 to 175 degrees centigrade. That is, even if you put these converters inside your vehicle, they have the capability to withstand higher temperature rise, which means the chance of failure due to overheat is reduced by 80%, because you will have a battery inside, you will have a converter inside, you will have a rectifier inside, everything is placed inside your vehicle, and that vehicle is closed. Now there is no free airflow to cool this, so that keeps on operating, and there is no concept like it will get cooled rapidly once you stop the vehicle. So now your devices should be able to withstand that high temperature, and WBG devices can do that for you. Now even you can use these WBG devices in charging stations. Now you should have a very efficient drive system and improve the efficiency of the converter. And besides this, if you concentrate on battery, so you have different options like SOC and SOH estimation, thermal management, efficient BMS development of your battery. Now, one more problem or one more feature that needs to be added into vehicles is, now if you go with any new kind of, not new, maybe some 10 years before, if you have bought any car or 5 years before, you can see that a fuel car, normal fuel car, a petrol car, you can notice that with the speed what you are going, with the fuel available, you can see on the display, the digital display tells you how many kilometers you can run in the same speed with the available fuel, right? That it is estimating the distance it can be traveled with the fuel available, and also it gives you what mileage you have covered or what is the present mileage with the same speed. So these are all the aspects that are available in the conventional ICE based engines or vehicles. However, when upgraded to battery vehicles, this feature is not yet added. You should check with the battery state of charge. So you should check how many points are there, like what you see in your mobile, 94%, 85%, 60%, 30%. When it comes to 50%, you should charge everything you should do. But with the available charge, you cannot estimate how much further distance it can go. So that concept of estimation of the drive cycle or estimation of the range can also be added into the system. Next, this V2G, G2V and V2V concepts are not, as of now, not valid in India, because see, V2G is vehicle to grid, grid to vehicle and vehicle to vehicle technology. That means in most of the Western countries, it is like it does not have a particular tariff throughout the day. In some times during the peak hours, the tariff will be very high, and during non-peak hours, the tariff will be low. In medium peak hours, the tariff will range between these two. That is, at 10 o'clock, if you see, as I said, that 10 o'clock, you'll have all the malls opening, all the shopping malls, all the offices opening. So there will be a huge demand. So in that case, if you consume, in that time, if you consume electricity, you will be charged, say, some 10 rupees. Whereas at 1 o'clock or 2 o'clock, there will be no much peak demand. In that case, you will charge, or you'll charge, say, some 8 rupees or 7 rupees. Morning hours, 6 to 8, 6 to 9 or 6:30 to 9. No shop will be open and no peak demand will be there. So that is low peak demand. And if you charge your vehicle or if you use electricity during that time, you will be charged only 4 or 5 rupees or 3 or 4 rupees. So at the same time, if you can input to the grid, you will get revenue for that. V2G is that concept. So if, during the peak hour, if you can discharge your battery to the grid, that is, your vehicle battery will discharge to the grid. In that case, you will get higher revenue. And during no peak hours, you charge your vehicle, that is G2V. In that case, you will pay less amount, but your vehicle will be charged. That is, I will sell my electric vehicle energy, say, at 10 rupees per unit, and I will charge my electric vehicle again at 4 rupees or 5 rupees per unit. So I'm getting some 5 rupees per unit profit. So this concept is not valid in India. It is valid only in few Western countries where you have something called dynamic pricing. And the next one is vehicle to vehicle. That is, in case where you have what you call one vehicle stopped at one particular point, say somewhere somewhere the vehicle is stopped, the electric vehicle is stopped. Now you need to charge it. Now you cannot take the complete charging station to that particular point. So what we can do is we can take one electric vehicle to that point, which is fully charged. Now you feed the vehicle which is stopped through this fully charged vehicle, vehicle to vehicle. You can transfer the electrical energy. So these technologies and the topologies related to these technologies are really the need for our. So you can, in case if anybody is interested in starting your research, you can do in this area. And I think in Delhi, some 1 year back, Nitin Gadkari has started this fuel cell bus. So that is another interesting area where we can work on. The problem with battery is, you know, after some 5 years or 6 years, after the battery lifetime, how to dispose the battery is one of the major question as of now. People have no solution for this, but people are still working on. So the alternative to this battery operated vehicles is fuel cell based electric vehicles. So this is one of the area. Dynamic pricing, as I said, this dynamic pricing you can work on for this thing. Location of charging station, using hybrid energy sources for batteries and for vehicles like battery and ultra capacitor. You can combine these two and use wireless charging, battery swapping stations, mitigation of EMI issues in converters and charging stations, and renewable based charging station. This is where we can concentrate more. That is, as I was telling you, the issues with a charging station like voltage instability, harmonic injection, all these can be mitigated using renewable energy based electric vehicle charging station. So you'll have your solar plant at a particular point and you'll have your charging station at nearby point, so that the complete the charging station will be run only on solar. And you may ask me now, sir, when it is completely run on solar, is it really enough to charge electric vehicle? Obviously it will be enough. And during night time, what to do? That we need to have some other alternative for that. Either you should rely on grid, or you should go with some again battery, or you should use some other technique to charge during the night time. So, and finally the last one is energy management in hybrid electric vehicles. That is, if you go with 2 or more sources, when to use what source. For example, most of you have already heard about, ultra capacitor. So the ultra capacitor charges quickly and discharges quickly, unlike a battery which takes time to charge and time to discharge. So when you need to climb a hill, or when there is a steep, in that case you need high power. So during that case, instead of battery, you use your ultra capacitor. So using ultra capacitor will help you in discharging more energy, that is climbing it fast. So now what happened during steep, based on the dry cycle, you should shift your source from battery to ultra capacitor and vice versa. So that kind of things can be tackled in energy management systems. So, and of course this charger. So these are the major scope for research in electric vehicle technology. So we are actually working on DC-DC converters using WBG devices. So this is what our project, what we are working in NIT-PY. So the design and development of high power density wide bandgap based DC-DC converter for 2-wheeler and 3-wheeler application. So we wanted to see this DC-DC converter, what we are working, it is only for auxiliary supply. So we wanted to reduce the size and improve the efficiency of the DC-DC converter, so that, and of course, when we do go with this WBG devices, it increases the lifespan of the converter also. Yeah. So why are we interested in going to this wide bandgap devices? It is because it is having higher breakdown voltage, so higher voltage operation, low on-state resistance, so lower conduction loss, and hence less heat dissipated. Similarly, higher temperature operation and thermal conductivity, so the device temperature increases slowly and the requirement of cooling will be reduced, and high saturated drip velocity, because of which we have lower switching losses and less reverse recovery time, and which allows us to go for higher switching frequency. So combinedly, we have the advantages of reduced losses, increased efficiency, size, cost, and weight will be reduced, and power density will be increased. So this is how we have framed, and our project objective is only to design a 500-watt DC-DC converter. So now, when coming to this new device, when we start working with a new device, we need to see what are the various devices available. So the various wide band gap devices available are silicon carbide, gallium nitride, diamond, and many more. So out of which silicon carbide and GaN have gained popularity because of their cost and size. And now we don't know how its switching characterization will be. So in order to study the switching characteristics of a device, we use something called double pulse test. So we use something called a double pulse test. So we have used this double pulse test using this LT-SPICE software, and we have seen the switching characteristics. And when we have compared the switching parameters and the switching characteristics, it has been observed that, so here you can see we have compared 4 different switches. One is silicon IGBT, one is silicon MOSFET, which are widely available in the market, silicon MOSFET, and GaN switch. So what is the time required for turning on, turning off? What is the total energy that is lost during the switching? This is what we have compared. Now you can see here a small, quickly I'll close this, don't worry. So here you can see the IGBT, it is having 221 nanoseconds as the turn on time, and a MOSFET 143. Whereas if you go with the SiC device, it is 120, and GaN device, it is only 34.2 nanoseconds. Similarly, all the comparison, it is shown that SiC MOSFET and GaN switch are very having very good performance indices when compared to the conventional silicon IGBT and MOSFET. So now we have shifted our research from silicon based devices to wide band gap based devices. Now out of these two, which one to be chosen? Again, another question. So we are actually going with 500 watt. So we have done all the work only for 500 watt. And for this, we have observed that silicon MOSFET is having a very high switching loss when compared to GaN switch. So we shifted to GaN switch. So we have also done this analysis in Plex software. So this is our rating. We have done for both SiC and GaN. So again, we have observed that. So this is a Plex software for GaN and silicon carbide we have done. And the important thing here we need to see is the heat sink temperature and the GaN switch GaN device temperature. It is somewhere around 49 degrees centigrade, and it is somewhere around 42 degrees centigrade in GaN. Whereas in SiC, it is 97 degrees centigrade and 62 degrees centigrade. That is, GaN have a very high thermal capability when compared to SiC for this 500 watt switch. And we have also plotted efficiency. Efficiency is almost the same in both the cases. And coming to the thermal analysis, in thermal analysis, we observed that GaN device is performing far better when compared to SiC devices for if you keep on increasing your wattage. So with respect to frequency, again, the GaN and SiC have been compared with respect to the junction temperature. As I said, the major reason why we have gone with this junction temperature and analysis on junction temperature, it is because you'll keep this DC-DC converter inside the vehicle where there is no extra cooling, where you have no option to provide any extra cooling. So we are more concentrated on the junction temperature. So we have used, or we have developed a small laboratory prototype. So this is the small laboratory prototype, and this is the driver circuit. And the major issues with this silicon carbide and GaN devices is that driver circuit. In silicon IGBTs and silicon MOSFETs, there is no much what you call parasitic effect that comes into the picture. So you can simply connect any driver circuit and you can easily do your things done. But in case of GaN and SiC, it is not possible. So I'll show you why this is more important. And here you see, this is the gate driver IC what we have used. I have given the number here. Gate driver IC, yeah, UCC 23313. This is the gate driver circuit. Now here, if you see, we have placed one small gate resistance also. This gate resistance, this initially we have taken in this capacitors and all, and that is in the testing phase. So we have not included all these things just to see what happens. So this, if you see this resistance, this is the gate resistance, and this gate resistance, yeah, this gate resistance is very, very important and plays a very critical role in the driver circuit. If this gate resistance is not properly designed, the loop inductance and loop capacitance, loop resistance comes into the picture, and the complete circuit will what you call behave abnormally. I'll show you that also. So this is what we have tested, a small laboratory prototype. Here you see, this is the output of the gate driver. It is very fine. But when you turn on the switch, the main power switch, this is how it happens. A small spike in the gate driver. So this is the gate driver output after you turn on the switch. Now, this is what I was talking about. So here you see, this is drain to source voltage. Now, in the drain to source voltage, actually, you should not have these kind of oscillations. It should be a straight line. However, these oscillations are occurring because of the so-called parasitic element and this loop inductance, and this concept we call it as ringing. This is called ringing effect. Okay, so this is one of the difficulty what we are facing now using these GaN switches. And if we connect the same thing using a conventional or silicon based IGBT or MOSFET, no such ringing effect is observed. It is all going smooth, but we are facing this issue. So this ringing effect. Now, after literature, we have gone through the literature to understand what and why it is happening. So we observed that we should place a snubber circuit. So we have placed a snubber circuit. So once we place the snubber circuit, you see that the ringing effect is reduced. There is no more oscillation. However, there is still a spike included. So we have this is the now we are working on to reduce the spike. The spike is too high, so we are working on to reduce the spike. And this is the output voltage. The output voltage is very simple and too good. So as I said, this is the issue we have faced. This is the drain to source voltage without snubber circuit. See, once we place the snubber circuit, no oscillations at all. It has come to a very it has come to the steady state at a very small instant, like very few milliseconds or nanoseconds. It has come into a steady state. However, this spike also should not be there. So we have operated at different frequency levels and we have observed these waveforms. Now we are trying to mitigate this effect. So this is what is regarding power electronics and its applications in electric vehicles. And to conclude, what we have covered is starting with the basics of EV, few power electronic converters in chargers and charging stations, and some WBG based devices, their switching characterization and the difficulties what actually one can face in using these things. So this is what is about electric vehicles and its power electronic perspective. So thank you one and all for patience listening, and thank you for giving me this opportunity.
Thank you, sir. I request participants to post their queries. Feedback link is already posted in chat box, ma'am. Please look into it. I request to post your queries in chat box, or else you can ask.
Hello, sir.
Yes, sir.
Hello.
Yes, sir.
Sir, good afternoon, sir. Shishidhar.
Yes, sir.
Hello, sir.
Yes, sir. Yes, sir. Please.
Yes, sir, it is audible, sir. Go ahead, sir.
Good morning, sir.
Good one.
Sir, I am asking that actually for designing any particular material battery, which is for fast charging, like that, any software is there, sir?
Sir, modeling you have you can go with your MATLAB. I'm not sure of the software which is available for battery design and modeling, but ANSYS has one. ANSYS has one separate what you call system for that battery design, and recently PSIM also has given this. The recent version of PSIM you can do with that.
Which one, sir? Which one, sir?
PSIM and ANSYS.
PSIM, that is actually, sir, battery, after battery coming over there, we can
No. You can have modeling of the battery then. Not see, you cannot go with what you call selecting a specific material and all, but battery modeling can be done there.
Battery modeling. No, sir.
Yeah.
I needed actually any specific material characteristic we can design along with the material battery.
I'm not aware of that because I'm not working on that. I'm not aware of that. Materials and all. I'm not aware.
Okay, but I have gone through one actually in a Synopsys. Synopsys, one of that software. I come across. I couldn't. I have not done and I am not aware of that one.
Okay.
So that I have asked this question. Sir.
Okay, I'm also not aware because I'm not working on battery design part. I'm just working on the charging structures and all this.
Okay. Okay, sir.
Yes.
Thank you, sir. Thank you very much.
Anybody else? You can post your queries in chat box as well. Sir, I would like to ask two queries, sir.
Yes, ma'am, please.
Hemchandra, sir.
Yes, ma'am, please, ma'am.
What is the difference between the silicon and silicon carbide devices, sir? SI and SiC. Now more research is moving into SiC devices.
Yes, ma'am. Actually, the band gap of silicon device, it is 1.12 electron volts, whereas the band gap of silicon carbide device, the band gap, it is around 3.3 electron volts, which means you are having more space for the electrons to move from one part to the other. So jumping of electrons. So this band gap is providing you high voltage capability. Okay. So high voltage capability in the sense it can withstand more voltage when compared to the silicon thing. And it also provides you high thermal capability, that is more temperature withstanding capability. So these are the advantages, major advantages of this. If you have heard through, if you have gone through this Google Little Box Challenge, somewhere in 2014 or 15, Google has conducted one Little Box Challenge. The challenge is design of a inverter, 2 kilowatt inverter in a very small size. It has given some dimension, less than the size of your notepad. In that case, what they have done is they have used these GaN switches, this silicon carbide and GaN switches. What happened is the power density of these switches is very high. That is, they can dissipate more power in a small space. So the size of the converter has drastically reduced from, as I said, from the size of a notebook to a notepad. So that is the advantages of these GaN switches, whatever the wide band gap switches.
So then, which is more advantageous, sir? SiC devices or GaN devices?
That depends on the power rating what you use. As I said, as I have presented, my work is on 500 watt system. So for 500 watt system and 500 kilohertz, if I wanted to increase the frequency, GaN is better. But if I wanted to go with higher kilowatt rating, in that case, silicon carbide is better. So if you wanted to increase the frequency, say till 1 megahertz or 2 megahertz, GaN is better for up to 1 kilowatt rating or 2 kilowatt rating. After that, the switching character, the what you call the thermal capability of the GaN will reduce and SiC will increase. So in that case, you can use SiC. So the application defines which one to use.
Okay, sir. Will it affect any gain factor, sir?
No, the voltage gain factor is what you are talking about.
Yes, the voltage gain factor.
No.
Whichever the device, it will be the same.
The advantage of switching at higher frequencies is the parasitic, the passive elements like inductor and capacitor, the size will reduce.
Okay.
Suppose if you are designing a 10 kilohertz inverter, the size of inductor, say it is some 2 millihenry. Say, if you go with 100 kilohertz, the frequency, the size of the inductor will be only 200 microhenry. Reduce. That is what the advantage.
Okay, thank you, sir. We have one more query in chat box, sir.
Yes,
can we develop charging stations in India?
Yes, we can develop charging stations in India. Maybe what exactly you wanted to ask is not clear for me. If you wanted to develop charging station for public charging station, like if you wanted to start your own business, Indian government is always ready to accept that proposal. You can approach any of the MSME nearby and you can give your proposal. They're readily accepting that. And as I have shown you, the ABB and Semicron, they are readily having this charging infrastructure, and you can go with it. And there are various public charging stations coming up in India also. In Kerala, if you see, there are many charging stations that are available. The Kerala State Electricity Board itself is running those charging stations for both two-wheeler, three-wheeler, and four-wheeler. And apart from this, the charging station in Kerala, the advantage is pole charging stations. You understand pole charging station. The pole charging station is nothing but to the normal poles, the power poles, you will have a charging station. That is, you can charge your electric vehicle there itself. That too, you find it in Kerala. You need not go to any foreign countries also. If you have some time, just give me 1 or 2 minutes. I'll show you that. Yeah. Just a second, I'll share my screen once again to show you a small video of this pole charging station. So this is a pole charging station which is established in, yeah. So this is a pole charging station where you can see so you can see here It is simply mounted to a street light pole. You need not do anything. You can charge two-wheeler and three-wheeler. Even if you go from, there are nearby places from Thiruvananthapuram, some 100 kilometers. In between them, there are some four-wheeler and three-wheeler charging points also.
Thank you, sir.
So this kind of charging stations, they can be installed in and around all places across India. Is it okay, ma'am?
Yes, sir. I think it is exactly.
Yes.
Can we have some more queries from the participants? Sir, I think there are no more queries. I would like to wind up the session, sir. Thank you very much, sir, for a wonderful session. You have started with introduction to EV and different bike models and charging stations. A lot we have discussed, and also regarding fast DC charging, and regarding the challenges with the development of charging stations, which is an important perspective, and isolated DC-DC converters, and in practical charges like Semicron Danfoss, and regarding wireless charging. So you have given a lot of inputs regarding research perspective as well, because everyone are research oriented. It is each and every point is useful if they really want to do their research in electric vehicles. So we are very much thankful for the wonderful session, sir. And we look forward in our future sessions also, sir. And in this regard, I would like to thank the college management, Chairman, sir, Secretary, and also Director Dr. J. Raja Murugadas, sir, for giving us this opportunity to conduct this event and make it successful. Thank you very much, sir.
Thank you, ma'am. Thank you for NSRIT for giving me this opportunity to share my views on electric vehicles. Thank you.
Okay.
Thank you, sir.
Ma'am, can I leave?
Yes, sir.
Yes, thank you.